energy, powering our nation, powering our economy. In 2006, AEP completed construction of its Wyoming Jackson's Ferry 765 kV project. This extra high voltage power line is the first enhancement of AEP's transmission system in over 30 years and the first 6-conductor bundle design ever constructed in North America. The project is 90 miles long and stretches from AEP's Wyoming station in the coal fields of southern West Virginia to Jackson's Ferry Station in southwestern Virginia. The landscape that the power line crosses proved to be some of the most rugged terrain to construct such an important project. All of AEP's previous 2,000 miles of 765 kV power lines were built with a 4-conductor bundle arrangement. The new line utilizes a 6-conductor bundle arrangement, and more wires means more challenges for the engineering and construction teams. Road construction proved to be its own challenge in the mountainous terrain of the 765 kV project. AEP constructed 164 miles of new or upgraded road along the 90 miles of right-of-way. A total of 262 miles of road were utilized, counting the existing private and secondary roads. The quality road construction created an access system that was reliable in adverse weather conditions and large enough for crane access. Tower steel was delivered to one of 5 central material yards across the project. For self-supporting towers, or those supported by 4 individual legs, the bundles of steel were delivered to the tower site by helicopter prior to assembly. The crew fastens the bundle of steel to the helicopter's electric grab hook. The pilot carefully lifts the load from the material yard. The steel is delivered to the tower site. Once the material is on the tower site, assembly of the structure may begin. Foundations are the first tower component to be assembled and installed. The excavation location is marked from the center hub of the tower. Once the excavation is complete, a steel box is lowered in the hole to protect the crew while the grillage is set. The bottom of the hole is prepared by tamping a flat surface and covering with a layer of gravel. The gravel is also tamped and leveled to evenly distribute the load from the grillage foundation. The grillage for a self-supporting tower is assembled and lifted into place. The pyramid design evenly distributes the load from the tower leg to the base of the foundation where it is resisted by the soil. It is imperative that the foundation is accurately set in order for the top of the tower to properly assemble. Adjustments are made. The survey is checked. Grillages proved to be very challenging to install in the rock found in mountainous terrain. After the grillage is set, the contractor fills the hole, tamping the soil as lifts are added. This compaction technique is necessary to give the foundation the uplift capacity assumed by the engineer during the design process. Gasoline-powered tampers compact soil in the larger spaces of the hole, while a smaller air tamp is used to compact the soil inside of the pyramid. the grillages are installed awaiting the erection of the mighty superstructure. After the foundations are complete, the legs of the self-supporting structure are erected, followed by the main tower body. Upon completion, the self-supporting structure is ready for use.
We've been at this project, as you very well may know, since 1990. We're finding ourselves at the 14th year of permitting, so it's very gratifying after going through that many years of the permitting process to find ourselves finally building this project.
The foundation system for a guide V structure consists of a center mast grillage that supports the vertical load of the structure and 4 guy wires that resist transverse and longitudinal loads. The center mast grillage is smaller than a self-supporting grillage, yet it is installed and functions in a similar manner. 2 hemispheres that support the superstructure are located at the top of the grillage.
The guide V towers are supported by 4 grouted strand anchors in the center mast grillage, and there's a great savings in foundations on the guide V structures because you're only utilizing 1 grillage, which weighs somewhere in the range of 3,000 to 7,000 pounds, in addition to 4 grouted strand anchors. So we save not only in material but in labor.
The ball and socket connection between the tower and its foundation lends itself well to tower erection, since it is easily guided to the final position. The guy wire foundation is a grouted strand anchor design, which consists of a bridge strand cable that is drilled in the earth and grouted in place. Its bond to the rock provides the resistance to the tower loads that translate through the guy wire. The grouted strand anchors are installed by first drilling the hole in which the strand will be inserted. Lengths may vary depending on how shallow or deep the rock layer is located. The bridge strand is centered in the hole by spacers located along its length. Here, the bridge strand is ready for installation with the white spacer and grout tube in place. The bridge strand is inserted and the crew pumps grout into the hole. The final product provides an anchoring system that can resist upwards of 275,000 pounds from the structure's guy wire. 70% of the guide V towers were erected using a land crane that simply lifts the structure up and into place. Many times, the guide V was set in components with the mast, or legs, set first. The crane is released from the masts and next lifts the tower bridge into place. Four pins, 2 on each mast, secured the tower top on its legs. The hinge allows utilization of various mast heights with the same tower top. Cross arms are added on each side of the bridge to complete the tower.
The current 765 system we have on the AEP system is built with a 4-conductor bundle arrangement. The new line that we're building today is built with 6-conductor bundle arrangement. So our challenge as structural engineers was to design a new tower family that can take into account the additional wires that we're putting on the structure.
Some of the structures on the project were set using the Chinook helicopter. Most of this type of erection occurred in the mountainous terrain of West Virginia. towers were assembled in a common area known as the marshalling yard. At this yard, 35 towers were pre-assembled and await delivery to the tower site. The tower steel was fabricated by Lockweld, located in Montreal, Canada. Lockweld etched a surface treatment on the steel to darken its appearance and allow it to blend into the landscape better than traditional galvanized steel. The helicopter lifts the mast of the guide V structure from the marshalling yard and transports it through the air. The mast arrives at the site where the ground crew awaits its delivery. The ground crew grabs the guy wires to help control the structure and move it into place. Next, the ground crew guides the bottom of the mast to the top of the foundation and then secures the mast using temporary guy wires. The load is released by the helicopter so it can return to the marshalling yard for the next pickup. The helicopter returns with the bridge of the structure. Guide systems on the mast and bridge add accuracy to the process and helps the pilot hit the target. Spring-loaded clamps grab the base of the bridge to stabilize it from tipping over. After the bridge has been seated, the pilot releases the load. Crews climb the structures to make up the permanent connections that fasten the bridge to the mast. After the structure is fully erected, crews install the permanent guys that will support the final structure and wire loads. The permanent guys are hoisted to the connection point in the tower top. The connection is made. On the ground, the other end of the permanent guy is wrapped with a guy grip. The guy wire and grip are wedged into a housing that connects a U-bolt to the foundation system. The U-bolt is torqued to put the proper amount of pre-tensioning into the permanent guys. The structure is checked to ensure that it is plumb. One of the most complex tasks in building the Wyoming Jackson's Ferry 765 kV project was the process of stringing the 6-conductor bundle to the tower. But before the wire can be strung, the hardware and insulation that attaches it to the tower must be installed. The hardware, including suspension clamps, compression dead ends, clevises, and yoke plates, were manufactured by Salvi in Milan, Italy. NGK Lock manufactured all of the insulation used on the project. Depending on the tower type, insulation can be either porcelain or non-ceramic, also known as polymer insulation. The insulation for suspension towers is provided in 50,000 or 80,000 pound polymer units, or 25,000 or 36,000 porcelain units. Insulation units are pre-assembled and hauled to the tower site prior to the installation crew's arrival and are ready to be lifted and attached to the tower. This crew is preparing a 50,000 pound rated polymer insulator assembly to be installed on a Guide V suspension tower. Using a simple rope and pulley system attached to a large truck, the crew hoists the insulator assembly up to the men on the tower. After doing this several times, the crew knows exactly how to position their rigging. Proper rigging techniques are a vital part of installation process, not only from a safety standpoint, but also to reduce the risk of insulator damage. Once the insulator assembly is hoisted to the proper position, the crew pins the assembly to the appropriate attachment points on the tower. Once the assembly is attached, the tension is released on the hoist ropes, allowing the insulators to hang in their proper position. Porcelain units require the same amount of care during installation. These dual-string, 36,000 pound rated units will be installed on a self-supporting suspension tower. Due to the weight of the dual-string porcelain insulators, a lifting apparatus is used to hoist the insulators up and into position on the tower. Prior to any insulator installation, the assemblies must be carefully wiped clean of any foreign material. This ensures the insulators perform as desired electrically. As was the case with the polymer insulators, it is imperative that proper rigging techniques be used in hoisting the strings into place. A skidder is used to hoist the assemblies into position. A final check is made to ensure the insulators are clean and that the connecting pins are rotated in the same position. Hoisting continues until the assemblies are raised to their final position and pinned into place. After the insulator installation crews have completed their phase of the project, preparations are made to install the conductor. This includes grading and leveling two areas called tensioner and puller sites that will be used to position the equipment that installs the conductor. Alcan Cable provided 8.5 million pounds of 795 kcm ACSR for this project. The non-specular finish on the cable minimizes the glare on the aluminum conductors, allowing it to blend in with the surrounding landscape. Reels of the conductor were delivered by either truck or helicopter. As seen here, the Boeing Chinook was used in the most rugged terrain of the project to transport the conductor reels from a marshalling yard to the tensioner site. These reels contain over 12,000 feet of conductor and weigh about 6.5 tons. Due to the extreme topography and remoteness, the Chinook greatly reduces the time and cost of getting the conductor to the remote and difficult site. The Wyoming Jackson's Ferry project was constructed using a unique 6-bundle conductor arrangement for each phase. The reels of conductor are manufactured in matched sets, each having the same tension history. Here is the Chinook delivering the last reel of a matched set to the tensioner site. The site contains the 3 sets of 6 reels and the necessary equipment to install the conductors.
Alcan was proud to provide all the electrical conductor on this project. We provided turn ACSR cable, and we're very proud to be a part of such a large North American project and to work with AEP and to partner with them on such a big undertaking. Transmission jobs are usually always significant to us in terms of volume, but this has been one of the biggest orders that Alcan has shipped, totaling over 8 million pounds.
On the other end of the pull is the puller site, where the equipment that will pull the wire through the towers is located. Stringing blocks, the key tool to make this process work, have to be hung on the towers before the conductor can be pulled. The blocks are large pulleys that the conductor travels in as it is pulled from tower to tower. Helicopters were used extensively to transport people, equipment, and materials to the job site. The Hughes 500 is used to place the lineman on top of a dead-end tower to prepare for attaching the stringing blocks. We believe that this 6-conductor bundle block is the heaviest stringing block ever produced for a transmission job. With its helicopter attachment and grounding rollers, the block weighs over 600 pounds. The helicopter picks the block up from a material yard and delivers it to the lineman on the tower. The pilot carefully lowers the stringing blocks down to the linemen, who maneuver it into position and attach it to the tower. This dead-end tower is the heaviest and strongest structure on the entire project. It is now complete with all stringing blocks installed. Conductor pulling can now commence.
This line is being built with a 6-conductor phase bundle, 6 conductors arranged in a circular configuration like a clock face. The conductors are at 1 o'clock, 3 o'clock, 5 o'clock, 7 o'clock, 9 o'clock, and 11 o'clock. This is different from the 2,000 miles of 765 kV that were built prior to this line. On those 2,000 miles, we used a 4-conductor bundle arranged in an 18-inch square. One of the benefits is less audible noise. This line will be quieter, and that's the first time this configuration is being built in North America.
The 6 conductor stringing blocks used on this project are a new and innovative design developed and manufactured by Sherman and Riley of Chattanooga, Tennessee.
Sherman and Riley's role was to design and manufacture conductor stringing blocks, grounds, helicopter attachments, running boards, and other accessories for the construction of this 765 kV line. We were honored to have the opportunity to do that. We think we have manufactured a very efficient and workable piece of equipment, as has been proven the several days that I've been here on this job.
We're the engineers and manufacturers of the special 6-conductor, 6-bundle transmission block currently being used on the AEP, American Electric Power, 765 kV transmission project. We designed this specifically for this job, and to my knowledge, there's never been another 6-conductor block designed. Not have been any 6-conductor transmission work done in North America. When the project was first known, we decided what we thought we needed to do, and then that is to supply a block that will allow the pilot rope to be flown in by helicopter with our Model HWA-70 helicopter wheel attachment, and with our barn doors or gates that protect the pilot rope and the hard line from entering to the conductor ship. This block is a 7-shift, 6-conductor steel frame channel with the hanger strap. The hanger straps are designed to attach to the upper holes of the yoke plate. By doing this, it allows the linemen and the installers to remove 2/3 or 4 of the 6 conductors once they are in place to transfer it to the insulator and or hardware chute. The last 2 conductors are then removed, and then the complete block is removed from the tower. But what makes this block so unique is the Pac-Man or the helicopter wheel attachment. As the helicopter flies in the pilot rope with a 45-degree outrigger arm, the helicopter operator drops the pilot rope in the 45-degree arm, and it slides down and trips. Once it trips, it allows the pilot rope to slide down the protected gate into the center groove. This protects the conductor groove until such time the conductor reaches the block. By allowing the pilot rope into the center groove, it is then hauled back to the main puller or the larger hard line, and then redone, repulled the hard line back to the tensioner end. In addition to the Pac-Man or helicopter wheel attachment, the block is also outfitted with a block ground. This ground that has a specially designed cam action articulation that allows positive contact on all 6 conductors regardless of the movement of the conductors. In addition, the ground has a 40-pound thrust against the conductors to also give it main and positive contact during the stringing operation. The ground is equipped with grounding lugs on each side that will allow the linemen to install their ground leads and attach to the tower or to other grounding areas of the transmission tower.
The lead line is installed from the pulling machine to the dead-end tower. The lead line is 5/8-inch diameter synthetic rope that is color-coded to represent each phase of conductor. The needle is an apparatus attached to the lead line to pull it through the center phase window of the tower. This operation requires patience and precision by the pilot. At structures with large line angles, the lead line has to be hand installed into the conductor stringing block by the lineman. Once the needle is passed through the tower, the helicopter continues to fly the lead line to the next structure or to the end of the wire pull, where the linemen secure it to an anchor point on the pulling machine. A similar process is used for the outside faces of the tower. Again, with precision and accuracy, the pilot maneuvers the lead line into the conductor block. The lead line is automatically placed into the block by the Pac-Man device as the gates feed the line into the center sheave. The efficiency of this operation was devised and perfected by Sherman and Riley. Here we see a similar sequence, but with the addition of the needle device used for the center phase of conductor. The pilot hooks the needle to the tower, releases it, moves to the other side of the tower, rehooks the needle, and proceeds to pull the lead line into the stringing block. To pull and place the main pulling rope for pulling the conductors, several graduated steps must be taken. First is the 5/8" lead line. It is taken from the puller sight through each block to the tensioner sight. Second, the lead line is connected to the 3/8" steel pilot line rope at the tensioner. Third, this pilot line rope is then pulled back to the puller sight. It is then attached to the 3/4" steel wire rope pulling line, commonly called the hard line. The hard line is then pulled through the towers back to the tensioner sight, where it will be connected to the running board and the 6 conductors. The next step is to prepare each of the 6 conductors to be connected to the running board, called the gator by the lineman. Flexible wire mesh pulling grips are installed over the conductors. These grips use the finger trap concept to grasp the conductor securely. The grips and conductors are then attached to the gator's rear swivels. The hard line and its lead swivel are connected to the front of the running board. These swivels allow the pulling line and the conductor to rotate under load without transferring the torque to the running board and the conductor. Here the connection is completed and the gator is released to the pulling position. The gator's stabilizing device is its tail. The tail prevents the gator from flipping and twisting the conductors. If the board flipped over, the pull would be stopped and the gator returned to the proper position by hand. The reels of the conductor are loaded onto a multi-reel trailer for dispensing. All 6 conductors are pulled with the reels and through a special machine called a tensioner. The tensioner consists of a set of bull wheels for each of the 6 conductors that pass through the device. The bull wheels allow individual control of the tension of each conductor with a hydraulic braking system. This allows the conductors to be pulled in a synchronized manner that maintains comparable tensions and loading history in the 6 subconductors. The tensioner that makes this possible was custom designed and manufactured for AEP's Wyoming Jackson's Ferry 765 kV project. The pull commences. The gator starts its journey as it leaves the tensioner and moves toward the first structure. The conductor feeds off the reels evenly. The operator controls the brakes on the reel trailer from his control panel, while he controls the tension on the individual conductors with the bull wheel brakes. This precise control of the tension ensures the conductors are installed to specifications. The gator approaches the tower and goes through the block. It continues to the next structure.
We're going to demonstrate here is the opening of the gates as the running board passes through, placing the conductors in the sheave. The running board would be right here, and it would push the gates open like that, then putting the conductors in each sheave.
The gator approaches a suspension tower. It pushes open the gates of the stringing block and places each conductor into the proper sheave. The gator continues to the next tower. This dead-end structure has a severe line angle that requires the use of 2 stringing blocks attached on each side of the tower. This double block arrangement reduces the breakover angle of the conductor, which reduces the strain on the block and, most importantly, on the 6 conductors. When the gator passes through a tower where the line angle of the transmission line and the elevation difference between towers is unusually large, the linemen slow the pull and walk it through the blocks. The pull proceeds at a very slow pace under the watchful eyes of the linemen until the gator is eased through the blocks. This technique allows the contractor to get through a heavy line angle and make a longer pull more compatible with the length of wire on the conductor reels. The pull proceeds until the conductor nears the end of the reels. The operator slows the pull and then brings the system to a complete stop. The empty reels are changed out and replaced by 6 new reels. Once in place, the new conductors are temporarily attached to the ends of the first set of conductors with back-to-back mesh grips. This temporary splice is slowly fed through the tensioner and secured to anchor points on the front side so a permanent splice can be made. The Wyoming Jackson's Ferry 765 kV project marks the first time AEP has used an implosive sleeve in transmission line construction. The implosive sleeve was designed and developed by Implo Technologies.
We are a designer and manufacturer of implosive sleeve, also known under the trade name of Ziconex. Implosive sleeves have been used in North America by the utility company in the past 30 years. Briefly described, implosive sleeve uses the energy generated by a small charge wrapped around the sleeve to do the compression action normally done by 150 ton press and the die set. The final results in a much better compression is a smooth, uniform, void-free, pure metallic sleeve which is fast to install, it's less than a fraction of a second, and most importantly it's consistent because every sleeve is equal to the previous one. Okay, AEP decided to use Ziconex on the 765 kV 6-bundle project as a splice to be pulled through the stringing block. This decision considerably benefit the stringing operation by making it faster and smoother, reducing the time and obviously the cost. The sleeve was allowed to be passed through up to 45 degrees angle, and this smooth operation made the stringing work much easier and pulling through longer distances, reducing the cost also, but most importantly reducing the impact on the environment. The sleeve were pulled through the steep angles, very steep angles, and there was no damage to the stringing block, nor the sleeve show any mechanical strains or defect.
After the detonation area has been deemed safe, the lineman cleans the blast residue from the sleeves and the conductors. The finish is uniform and consistent. The spliced conductors are released from the anchor points and put back under tension. The pull commences. Implo's splices can pass through the stringing block without distorting or bending the sleeve, while traditional compression sleeves must be protected if passed through the block. Commonly used hydraulic compression sleeves are not capable of traveling through the blocks without deforming. These sleeves save a great amount of time and cost by eliminating the extra steps required when using older hydraulic compressed sleeves. 6 of Implo's splices can simultaneously travel through both single and double block setups on heavy angled towers with no deformation of the sleeves upon exiting. The pull continues until all 3 phases of conductor are installed. After the conductor reaches the last structure, the pull is stopped. The 6 conductors of all 3 phases are temporarily attached to the tower with grips and hoists. At this point, the conductors are sagged to their correct tension by using hoists. Once all the conductors are sagged, they are permanently attached to the tower. A conventional dead-end body is installed on each conductor at one end of the wire pull. The dead end includes a steel eye that is pressed onto the steel core of the conductor, after which the aluminum body is slid over the steel eye section and compressed to complete the assembly. For the turn conductor, the aluminum portion of the sleeve carries the current and approximately 64% of the tension, while the inner steel core carries approximately 36% of the wire tension. After all of the dead-end bodies have been installed, the conductors are then attached to NGK Locks polymer insulators with hardware designed and developed by Salvi. The hardware consists of suspension clamps, compression dead ends, and a series of clevises and yoke plates. Once the insulators are attached to the dead-end bodies, the entire assembly is pinned to the tower. A pre-assembled set of polymer insulators with its associated hardware is delivered to a dead-end tower for installation.
Now our work here is get all these regular and high angles towers clipped. What are we doing? It's hard. We just picking up the wire. Before we pick up the wire, we have to make some marks. We call offsets. We're going from the center of the picking point, whatever the offset call. It's got to be, you know, back line or head line. All depend what they want, and all this offset depend too how long is the span you're gonna pull on it, and get those bells plumbed. We got to use a clipping block. The one is good for 95,000 pounds, and we got to use jaw plate and different size of straps. What do we try to do? When we pick him up the wire, we try to pick him up in just one shot and get the same dimension of the jaw plate. It's a different rigging on the regular tension and the hard angle. For the regular tension, takes about, for phase, about 40-45 minutes. We don't have to put armor rods on this line, so that'll save us a lot of time. Head angle take about from 1.5 and 2.5 hours. All depend of the angle, you know, the degrees, and how low is going to be the span and the offset we're going to be working. Also, we take the block out of the wire, and we fly them with the helicopter. Now we are doing everything with the helicopter, everything. We move the ladder, it's a 30 feet long ladder. We move the blocks, and we move people from this tower we're clipping right now to the next one. Actually, we got to look for a couple things like how the bundle looks. If we have to adjust any of the wires to make it look before the spacing coming, we do it too. Also, we got to make sure if those bells are plumbed before we move to the next tower.
Once all the conductor is pulled in, sagged, and attached to the dead-end towers, it is time to clip in the conductor on the suspension towers. The clip-in involves raising the conductors out of the stringing blocks and attaching them with suspension clamps to the yoke plates. This places the conductor in its final position. The linemen measure and mark the offset distance on the conductor. This distance is measured from a plumb line from the center of the tower crossarm and designates where the suspension clamp is centered before it is tightened to hold the conductor in its final position. The lifting yoke is a special device used to raise the conductors in the correct orientation and position. The crew works to attach the yoke plate and readies to lift the conductors into place.
We go from left to the right, head on line. The first wire we call number 1, 2, 3, 4, 5, and 6. On this bundle, you know, the wires are going to the center. The numbers 3 and 4. Okay, the ones that are going on the bottom, they're 2 and 5, and the one on the sides is 1 and 6. So the rigging actually, you know, it's going from the jaw plate to the wire. The ones that are going to the top, 3 and 4, we use straps 2 feet long. The ones that are going on the bottom, we use a strap of 6 feet long, and the ones that are going 1 and 6 that are going on sides, we use straps about 4 feet long. So that'll keep us the bundle right where we need it. And it'll be, I mean, probably close to the jaw plate, so we don't have to fight too much to pin the tube or the clamp to the jaw plate.
Once the straps of the lifting yoke are attached, the conductors are slowly lifted out of the stringing blocks and into position. After the conductors are clamped into the suspension clamps and pinned to the yoke plate, the stringing block is raised, unpinned, and moved away. The Hughes 500 carries the stringing block back to the material yard. After the conductor clipping is finished, the linemen attach grading rings to each side of the yoke plate. Grading rings are used to reduce the electric field intensity on the hardware in order to prevent occurrence of visible corona, radio and television interference, and audible noise. Once complete, the clipping crew and their equipment is transferred to the next tower. The final phase of the process is to install the spacer dampers. A spacer damper is the hardware that attaches mid-span to all 6 conductors at intervals ranging from 100 to 200 feet. The The spacer damper holds the conductors at the designed 30-inch diameter conductor circle. The device dampens and removes the vibration effects experienced during certain environmental conditions.
Our product, our spacer damper, has been designed specifically with the 765 kV 6-bundle conductor arrangement in mind. We've put a lot of design effort into the control of aeolian subconductor oscillation with the spacer damper, and we believe that with the combination of design for the high voltage application and the vibration control, our spacer damper is amongst the best in the world.
The spacer buggy is a special in-air working platform that is placed on and rides on the conductors. The 6 conductor units seen here were custom designed for this project. The buggy is placed on all 6 conductors via cushioned wheels and is powered by a small gasoline engine that propels it along the line. The linemen work from inside the buggy to install the spacer dampers. The Hughes 500 delivers the spacer buggy to the linemen. The buggy is positioned so the linemen can place the wheels to the conductors. The helicopter again saves time and expense by eliminating the extra men and equipment needed to access each tower site to lift the buggies and material up to the linemen. Once the buggies are in place, the helicopter goes to the material yard and picks up the hardware to deliver to the linemen. The helicopter supplies enough spacer dampers for a span of conductor. Once all the spacer dampers have been delivered, the 3 linemen are ready for the installation. The buggies have a distance counter mounted on one of the wheels that measures the design interval between each spacer damper. The 3 buggies can travel in unison as the installation proceeds. A special tool is used to squeeze the 2 sides of the rubber-lined clamp together. The clamp is pinned in place. This process continues until the next tower is reached. At this point, the buggy is transferred around the suspension assembly to the other side of the tower. Transferring the buggy across the suspension assembly takes approximately 20 minutes. More spacer dampers are delivered and the installation continues. At the end of the day, the linemen secure the buggies for the night and call for their ride back to the material yard.
I think this line is an example of how AEP tries to use the latest technology to do the best job we can, to provide energy to our customers, and to do it in a way that's least detrimental to the environment. And that's the spirit of our employees, that's the spirit of this project.
This ends a full and productive day of constructing the United States' most powerful electrical transmission line. Power for our nation, power for tomorrow.
Another incredible great day for the people of American Electric Power. Now, I know all of you couldn't be here with us, but for those who were, this is one of those great celebrations that you get to do once or twice in a career. And that says a lot about who we are at American Electric Power. To have the governors here, to have Congressman Barton, the chair of the Commerce Energy Committee from the House. Incredible amount of work of the people of AEP, something for all of us to be incredibly proud of. I wish that you could have all been here, but at least through this video, you have a chance to share a bit in what we all did today. Something that we should all be deeply proud of, and thanks to all the people who did this work.
It's a good thing that demand is growing for electricity, because it means that America is still growing. These kind of power lines are going to be needed if we're going to keep up the economic growth that we're experiencing.
This project will have an immediate benefit come June 30 in providing reliable electric service to this part of the state, to West Virginia, but also being part of a national grid, a national power grid that can provide reliable power through our nation, which is something that the entire economic kind of operation of our nation depends upon.
We're thankful, really are truly thankful, Mike, for the investment AEP has made and the commitment that you have and the confidence you have in the state of West Virginia and our state of Virginia that we can work together to make sure that we all become good corporate neighbors and partners
I just want to say this is a very important project. It's been recognized as such for a long time. This is my first facility dedication as a FERC member. We've gotten invited to other facilities, but I've saved my first dedication for a big one. There's been a sustained period of underinvestment in the U.S. transmission system. We might be turning a corner on that, but there has been many years of underinvestment in the grid.
We're going to take the time now to move into a very unique part of this undertaking. The events that are going to happen today are splicing the last splice along this incredible 90-mile route. We've spliced over 1,008 connections, and today we'll do that last one. And, you know, when you think in terms of a historic event, some years ago as this country built the interstate rail system, they always had the final gold spike, which connected the system and allowed for commerce to flow. And today what we'll do with our friends from Quanta is to take a look at how we physically do that.
Well, now, without further ado, ladies and gentlemen, I present to you the final splice of the Wyoming Jackson's Ferry 765,000-volt transmission line.
I think that anyone working for a quality company such as AEP should be proud. They should be proud of what they're offering to the country. The energy that they're keeping this country strong, the energy that's made this country strong, and will continue to keep it strong.